I'd like to give you a brief overview about our company, Bilge. The name of our company, Bilge, stands for Field Generation. The company was established in 2013 by Dr. Lee. Last year, Bilge was selected as a promising venture company by Kaibo Technology Fund. We are a leading research company in full-scale computations for a ship. The overall talk consists of 3 parts. Firstly, I want to start by giving you our software development. Second, I am going to talk about practical applicability of our software, Grid Generator, in ship design process. Finally, I want to introduce energy-saving devices for ships, independently developed by our company, and emphasize on their effectiveness. Let me introduce the software for structured grid generation and RAN's flow solver. Novel elliptic partial differential equation method for grid generation has been developed to improve grid quality over complex configuration. The method provides the desirable quality of smooth grids with good orthogonality and ease of control of clustering. It does not divide the block to generate the grid in the flow field. This is one of the main advantages of this grid generator, allowing a fine structured grid around the whole vessel, even with complex energy-saving devices attached on its surface. The following is an introduction of our flow solver. The governing equation is Reynolds average Navier-Stokes equations. Higher order finite analytic scheme was used in the numerical solver. The turbulence model used is modified Spellart-Almaraz turbulence model. There are 2 main features of our flow solver. One, flow computation performed in the moving grid, and the other, physical coordinate system that accounts for the velocity field. The great advantage of this coordinate system is the almost perfect conservation of mass and momentum, even in the presence of coordinate distortion around 5 degrees. The effectiveness of the present numerical solver together with our grid generator has been validated under a wide range of ships throughout many years. Ship design engineers need reasonably accurate estimation of power. For this reason, CFD is indeed a practical tool for carrying out development and evaluation of hull form in the ship design process. Together with our high degree of technical design knowledge and our advanced CFD technology, we can fully support the needs for ship designers. Also, a commercial code can be used for the flow computation. Here, we show how we can actually provide accurate and informative numerical results for ship design in both model scale and full scale. This figure illustrates the pressure distribution on the surface of the hull, propeller, and duct. The force was computed on the hull surface with propeller rotation. Thrust and torque was also computed on the propeller surface. Computation was carried out in model scale. Extensions to full-scale method was applied to ITTC 7/8. It can be seen that the RPM and power is good agreement in the 3% range. Resistance is a 1.3% difference. The full-scale computation is performed in the following 3 cases. First is a precise powering performance evaluation of the energy-saving device. Second is optimal design of trim under draft and speed conditions. Third is flow computation in consideration of the surface roughness. Undoubtedly, this is the best way of utilizing CFD at present. An accurate prediction of trim is quite important because there is a fuel optimum trim. CFD simulations in full scale are recommended to assess the best trim. By changing the trim in the 6 different speed range computations were performed at full load and ballast. This figure shows the calculation results in a full load. Black line represents the even draft. Stern trim requires more energy up to 5%. However, bow trim shows energy savings of 1% in the full speed range. Next figure is a result of the calculations in the ballast. In this case, you can see the advantages in the stern trim when having more than 21 knots. The computations were carried out at different hull roughness. The U-velocity component distribution on the propeller plane is different from each other. Also, it shows different streamlines on the cross sections. Finally, we introduce several promising energy-saving devices for ships, independently developed in our company based on our own software package. Our first energy-saving device to introduce despite of primal intention to reduce noise and vibration actually turns out to reduce unnecessary waste around the ship as well. When the vortex starting at the bilge area passes through the propeller plane, it generally gives bad influence on the propulsion efficiency. Mainly it occurs in the low-speed ship. This device reduces the vortex generated in the bilge, straightens the flow, and reduces the boundary layer thickness. Energy saving of this device is about 2%. It can be used for both new building and repair shipbuilding. These are examples of the vortex generated at the propeller tip. The suction side tip vortex is observed. The trajectories of tip vortices were calculated by using time marching method. Tip vortices are produced from the moment of fluid caused by the pressure difference. This high pressure zone in the propeller plane is mainly observed in the region between the 10 o'clock and 2 o'clock. Pressure distribution of the low negative pressure is also observed in the same areas. The figure on the right side shows the velocity distribution changed when attaching this saving device. Blue at the end position near the propeller denotes a zero speed. In other words, a U-velocity is zero in this area while the flow rotates. Another way of energy saving is reducing energy losses due to tip vortex. These are examples of hub vortex. The hub vortex is formed by the combination of the individual vortices shed from each blade root. Illustration of a case of attaching the reduction device is in the right hand. While the propeller is rotating on the clockwise direction, it normally causes to flow also in a clockwise direction. However, the direction of flow can be controlled due to the device. The following figures show a difference in the presence or absence of the reduction device. This vortex is relatively strong and can be dangerous because it can lead to erosion of rudder located in propeller race. These devices can get rid of these vortex generated around ship. Consequently, it can also contribute in reducing vibration and noise. The difference can be clearly observed in the clip. Smart duct places in front of propeller location. It reduces swirl motion generated from bilge area. Also, it controls the secondary velocity vector through the device attached to the duct. Thereby, it can improve propulsion efficiency with favorable velocity distribution. The Smart Duct is an energy-saving device developed for full-form slower ships. One can observe a change in the speed vector at propeller plane. The device is mounted on the starboard side of the duct. This duct combines a wake equalizing duct with pre-swirl plate on the starboard side of the duct. The effectiveness may depend on local flow details like the strength and position of the bilge vortex. The achievable power savings from the Smart Duct are strongly dependent on hull shapes and ship speed. The power saving for the ship is about 3%. This concludes the introduction of energy-saving device. Thank you for your attention.